OK, might as well get going. Hope homework 3 is not killing anybody. It is due today. We will have more TAs today. We're going to have some TAs later this evening as well. I think starting at around 9 p.m. there should be a TA or two in the lab. Again, if you're having some issues and you have a legitimate reason you need an extension, let me know. Email me. If it's, well, I just couldn't figure it out, that's probably not the best excuse. But if you can't get to office hours or something, let me know. I'm sure you can come up with something that I'll believe. You can put it that way. That's probably true. All right, so today we're going to talk about these things called priority queues. It's actually a kind of a different way of looking at the data structure world in some sense. We are going to first, before we do that, talk a little bit more about homework 3. So first things first. If you've tried to use provide and it failed on you and it said something like not enough files or you didn't have enough files, this is the reason. You need an extra backslash on the provide line that says like make provide in the provide in the make file. You need an extra slash. Let me show you what I mean. Let's see, assign data structures, assignment 3, original. Oh, hang on, let's see. Oh, I don't even have it. Yes, I do. More make file. OK. See this line right here? This is a mistake. There should be a slash there. There needs to be an equivalent slash right here. And then what it's doing is it's ignoring readme.txt and makefile. So it's not actually setting those in. So you need to put the extra slash right here. Make sure there's no space after that slash you put in there. And then it should work fine. Whether it compiles and all that is fine. There's no space there. I don't think there is, and I don't think there should be.
No, on the first event.cpp, event.hbase.
Yeah, there's a space here. There should be a space here and then a backslash. And then the rest of this should be the same. OK? Yes?
Is it bad that I added the slash after the second line and then slash after the makefile?
That's OK. That should be fine. Yep. If you added it after here, too, that's fine. Yeah, OK. But if you have more problems with compiling, like making and doing provide, let me know. That should not be the sticking point of the whole thing. OK? All right. Where were we? So we're going to talk about that. Got a UNIX tip of the day. Who asked me about this UNIX tip of the day? Somebody, it should be somebody in here. Yes, thank you. Asked me about the name again? Ethan, right. Ethan said, hey, I want to do this tip of the day, and I wanted to see this. And it's kind of cool. It's actually a pretty neat tip of the day. In fact, Ethan reminded me that of this, when he said, hey, let's do this, that reminded me of something that allowed me to use it for not this program, but what the program uses for today's assignment. So thank you very much. You will see that a little bit later. OK, we're going to talk a little bit about GDB and debuggers. I've mentioned this to a couple people. So after helping a lot of you guys with your code, besides my eyes bleeding a little bit, I've realized how important it is. And this is not a fault of yours. It's a fault of me reading too much code. Like that happens, right? If we can get you guys to use debuggers correctly, it will make your life a heck of a lot easier, and it will make my life easier and the TA's lives easier because you'll be able to find your bugs easier. OK, I'll show you. I won't actually show you in here. I think on Monday we're going to do, or Monday, Tuesday we're going to do a lab that actually uses debuggers and kind of shows you how to do this stuff. Who in here has come into my office hours and I've thrown the stuff into the debugger for you? A couple people, right? Yeah, a few people, and that helped. I mean, we were able to find the bugs relatively quickly, I think, in most cases. If you have, well, we'll talk about it in a minute or so. And then finally, we're going to talk about these things called priority queues. I'm going to go relatively slowly in terms of describing them, and then we're going to get into some code, and I'll show you what they mean. And we'll actually follow this through with some more priority queue stuff after spring break, actually. OK. Any questions before I begin with the UNIX tip of the day? All right. So, whoops. So Ethan said, hey, would you like to, why don't you show everybody this cool tool called aspell, right? And here's what it is. I don't know if you guys know this, but your Linux computer, in fact, your Mac as well, in the cd/usr/share, I believe. I think that's where it is. Oops, what is it? cd slash user slash, is it share? Yeah, user slash share slash dict, as in dictionary. In that folder, there is a file called words. And that words file is a dictionary of American words, right? Let's see, less words. And it starts off with a bunch of like numbers and whatever, and then eventually gets into all the different things that it thinks are words. Now, A, is probably not a word, but I guess enough people use it that it gets into this dictionary, right? And it goes through all these things. And on the Linux computer, this, if we do word count to tell how many words, that's another UNIX tip of the day, word count, words, it will tell us that there are 479,623 words in this document, which is a lot of words, right? But that's actually like the Webster's dictionary plus some other special words in there that is in there. And what's cool about that is that you can actually use that to let's say, do a spell check, right? There's this command called aspell. And if you do aspell check and something like maybe your readme file, .txt, it will come up and it will bring your readme file up, right? Like this. Actually, you know what? I did this earlier and I'm not sure. Hang on. I want to ls-al readme star. Yeah, move readme.text.b. I did this earlier and actually, there we go. OK, so here's what we're going to do. We're going to do aspell. So somebody's code, I don't know whose it is, or somebody submitted a readme file for the last assignment. And aspell check readme. And what it does is it brings up the file, and it just starts highlighting things that it doesn't think are words, right? And all you have to do is hit the I button for ignore, and it will ignore that and find the next thing. Now, some things it's going to find that you definitely want to ignore, like .cpp. Although it's not a word, you want to ignore it. You don't want to change it to anything. Event.pcp would be bad, right? Right? But you just hit ignore, and you hit ignore, and then eventually it will find something that you go, oh, wait a minute. That's not what I meant. I did not mean ECT, right? I actually meant ETC, which is what the first suggestion is. And you hit the little 1 button, and it replaces it with ETC and goes on and finds the next thing, which is kind of cool, right? So let's see. Ignore, ignore, ignore. Oh, there's another one, right? Same thing. The person really meant ETC, and it's going to give them the suggestion. What I think is kind of interesting about this is, what do you think the data structure might be that's backing all of these words? A try, maybe, right? Because it's almost exactly what you're trying to do, no pun intended, right? Is you're trying to find the words that have prefixes or something similar to this word. And one of the ways to do that is to go down a list and say, OK, let's see, what words start with E and are 3 letters long? Well, there's ETC, that might be it, or maybe EXT or whatever. And then it starts doing some other algorithm where it says, what are words that are close by? Like ECT, well, CT is close by, EC, et cetera, et cetera. You see what I mean? No pun intended again. But the point is that there probably is a good use for a try in this data structure that backs this up. OK, so let's see. We will, in this case, I'll hit 1 again to replace that one. I'll ignore, ignore, ignore. Lots of these ETCs. Ignore, ignore, ignore. Event node's OK. Schedule events. Oh, what's this one? Proceeds. Right? Too many C's. Well, you just look, oh, it happens to be the first one. This is a pretty good algorithm. It actually guesses for the first one pretty well most of the time, right? There, and then ignore, 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 transferred. How many R's should it have? 2, right? Transferred, right? OK, anyway, so on, and you can do that. And then when you get to the end, it just quits out, and it saves your file with the spelling changes, and you're all set. And then when the TAs read your README file, they don't say, spelling mistakes -1, which they could.
Can you do that?
Sure, they could. Your README file needs to be proper English. Sure. Why not? I mean, what do you think it's supposed to be a README file. Trust me, when I actually am looking through README files and it's like got spelling mistakes in it, I'm like, who wrote this? It's going, not yours. I mean, yes, yours too, but like in real ones, like real README files. I think, what's going on here? You don't want to look unprofessional. That's what it's all about, right? I mean, a README file in that case. You want to make it look good. Questions on that? A spell? Thanks, Ethan. Good suggestion. All right. What just happened? I got an email. I wanted to close out of that. There we go. OK. All right. So that was the UNIX tip of the day. Let's talk for a minute about this debugging thing. I have said this how many times in here that I know debugging is hard. OK, I have a hard time with debugging. Those of you who come to my office hours can tell. I'm like, I don't get what's going on, right? I mean, you have to be able to read code, and you have to be able to do it, and you get better over time, but it's hard. The lab demonstrated that, that reading code is not impossible. Obviously, you can read other people's code if you have to. In fact, sometimes it's easier to read other people's code than your own, just like it's easier to proofread somebody else's paper than your own, because you wrote the words in your own stuff, and you wrote the code, and you kind of skip over stuff that you like, oh, I looked at that before, right? But that might be exactly what you need to look over. Whereas if it was somebody else's code, you wouldn't, which is not a bad, which is why debugging with friends is sometimes a good thing. OK. Anyway, homework 3 has shown that when you have lots and lots and lots of cases, like 800 different events that you're trying to insert into some calendar, it's kind of hard to say what's going to happen at the 720th event, right? Because you're going through and you're like, I don't know what the program's got already. I don't know if I've screwed something up earlier or later or whatever. Well, although you need to be good at debugging code, if you use these debuggers, right, and GDB is a version, it's a debugger. That's the free one you get with Linux. DDD is is a graphical front end, which I've showed you before. Remember all the links that I showed on one of the days? That's DDD, and it uses GDB. And you can use that. For anybody who has a Mac, there's a great debugger. Actually, it's called an IDE, which stands for Integrated Debugging Environment, I think. And what that does, that actually puts your code, all the files in there. You can hit go, and you can put these things called breakpoints, which stops you at an exact line of code. And then you can walk through the line of code, one after the other, until you find the line that's the problem. And it will do it for you. And the best part is it will show you all the variables and what they're all set to. It'll show you all the pointers, where they're pointing to. It'll show you. And you can, once you learn how to do this, it actually makes code debugging so much faster, right? You could, for instance, say, hey, it looks like event 63 is having a problem. Well, if you do a breakpoint such that it stops right when it gets to event 63, then you can go, OK, what's going on here? Oh, my day list is screwed up. Oh, it never expanded right, or whatever, right? You can look at, oh, let's see. And if you go through, you can figure it out. So it's a very, very important tool. Okay? And again, if you have a Mac, you can download XCode for free. You can certainly download DDD for free. And you can use these things, and they're completely free. It does take a little while to learn how to do them. That's kind of there is a bit of a learning curve. Question? No? Anybody else questions on that? Yes?
So this is a program that we download and then we copy and paste our code into?
Kind of. Let me just show you. I'm not going to show you the exact thing. But this is what I've showed you programs from this before. This is what XCode looks like. Right? It has all your code over here. And what you can do is you can copy and paste. If you have an SFTP program, you can get the files onto your computer. You can drag and drop them straight into this window once you start a project. And they're all here. And then if I wanted to stop when I got right here, right, I just click right there. And that's a breakpoint. That means stop at that line. And so when I run this, actually, I'm not going to be able to do it quite the way I want to here. But let me see. Let's see, 413, you can't see it, so it's blacked out down there. But you see, -1, and done. OK, so there, boom, it stopped right there. So in other words, it's gone through, and it's gotten to this point, and it's stopped right there. And I can actually hover over that and look, hey, MinIndex right now is 32767. Well, it hasn't actually started it yet. If I go to the next line, you can jump straight to the next line. And now, let's see, MinIndex should be 0. It is. Right? You can hover over there. It tells you that. Right? Let's see. What's my size? Oh, my PQ size, my priority queue size is 1. Right? My priority queue. Let's see. If I go up here, my priority queue. Oh, look. There's the pointer to it. That's where the pointer is. Oh, no. I click on here. Hey, it tells me that the key is 413. The element is ABC, which is what I typed it. So you see how this can become useful? Like for the event debugging, it'll tell you the whole event right there and say what the description is, what event it is, what start time, end time. It's great. Okay, so it's a bit of a learning curve to get this, but once you learn it, you'll go, oh wow, what did I ever do without it, right? And I hesitate to introduce it to you because then you'll rely on it and use it as a crutch, but I don't want you to do that. Yes, question.
So if you're accessing files with SSH to the Linux computers all
Yep.
How would you drag and drop from there?
Yeah, good question. So you have to be able to get the files onto your computer, which means you can download a program. Like I happen to have one called CyberDuck, right? And it's a little duck. You can't see it down there, but it's a little duck symbol. And what it does is I can actually, here's all the different ones, all the different folders. Let's see. Oh, yeah, it just automatically connects me to the thing. And then this is just like a file thing. In fact, I can just drag files straight around and drag them and drop them onto my desktop. So it's real easy to use. Okay, things like that are available. Okay, so once you get it on your computer, then you can do it. You got to remember to put it back on the Linux server, but other than that, it's not too bad. What's that? That's fine. SCP, whatever you want. However you want to get the files to your computer is fine. Yes, and you can also download the zip file from the website too onto your computer and then do it that way. Lydia.
Is XCode only for Mac?
Xcode's only for Mac.
You happen to know of any PC?
So if you're on Windows, I believe you can get Visual Studio for free through the university. It's normally like $1,200 or something. But through the university, I think you can do that. Now, that's also got its own learning curve, and it doesn't use Clang, so some things will be a little bit different. Mac happens to use Clang, so that's it. But it's also, let's see. Somebody would kill me if I said this, but there's Eclipse, which you can somehow shoehorn C++ into. There's some other debuggers that are good. On the top of my head, I don't know. I mean, best free IDE Windows, right? I mean, like I would Google this thing, right? What's the best free one? Oh, look, it's Stack Overflow, right? What? Right, Stack Overflow. What's the best one? Let's see. Not constructive. Well, I don't think so. Visual C++ Express. I think that one's free. GCC. You can use that. So yeah, I mean, you can get DDD and whatever, but there are lots of different options anyway. Okay. Yeah.
What about the Halligan computers?
Halligan computers use DDD, which is not an official, like it's not quite as streamlined, but you can do it. Okay. You can use it right from the terminal in the open up a terminal, type DDD, and it'll pop up.
Okay.
Yep. And again, I think next week we'll try to show you how to use DDD a little bit, so at least you'll get a little picture of that. Okay. Questions on that? Again, some people say never show students debuggers until they're great programmers because they'll use it as a crutch. But my feeling is at this point you can start to use debuggers. You're probably mature enough, all right, to start using debuggers. Okay. I talked about breakpoints. You can stop the execution. You can see what all the variables are. Blah blah blah. Questions on debuggers? Okay. Good tool. Okay. Let's start talking about these things called priority queues. Okay? A lot of times, both in real life and in programs, we want to prioritize certain groups of things. Okay? In real life, that happens all the time, right? Emergency room waiting rooms, right? Anybody ever broken like an ankle or a wrist and gone to the emergency room and sat there for like 4 hours before anybody actually sees you, right? Like the nurse will be like, oh, come on in, fill out this paperwork, and then you won't talk to another nurse for like 4 hours, right? It's because broken ankles don't kill you generally, right? Whereas the guy who's like accidentally sliced his hand off, like trying to cut the roast beef or something, he's going to get seen before you because he might bleed out, right? It's a priority thing. It's all about priorities, right? And that's the way real life works. Professor Hescott, who some of you guys know, said that gave me this example. He said, look, your office hours are kind of a priority queue. Not necessarily for students. I generally try to take students on a first come, first served basis. But if another professor walks in, I'm probably going to say, hold on a second, talk to the professor for a minute, right? That's the priority, because the professor's like, came by to say something to me or whatever. Department chair walks by. I mean, if the president of the university came by, you and I would probably stop talking and we wouldn't be like, hold on, whatever. Not for more than a minute or so, right? It's all about priority, right? And who has the priority for talking to you in that case? Getting on an airplane, classic example of priority, right? So when you get on an airplane, if you want to go like standby, there's like 7 different things they take into consideration about when to put you on the standby, like where to put you on the standby list, right? If you're first class, you bought a first class ticket, you're going to go on automatically, right? Like you're probably going to bump some poor schlep off who didn't buy a first class ticket, right? Because you paid so much. This is actually not the example. This is just the example of getting on the airplane. First class and families go first, then frequent flyers, then by row, et cetera, et cetera. But in terms of standby passengers, if you happen to be a frequent flyer, if you happen to have purchased an expensive ticket, if you happen to check in early, all those things take their priority, right? Getting on airplane is an interesting one. There's been a lot of research, like airline companies like pay for people to research how the best way to get on an airplane. Like, how do you get people onto an airplane fast? Because it's slow to do that, and they don't want to waste time. Especially for some of these planes. Like some of these planes have like 500 people now. Like these giant Airbus things. They have like 500 people. How do you get them all on at the same time? And there's been various studies. Like some airlines actually say, I've seen this one before. They say, if you don't have any overhead carry-on, if you're just carrying on like a purse or a small bag you're going to put onto the seat, you can go on right now. And they just let everybody on. And that just frees up a whole bunch of people who aren't like, stuffing stuff in the thing. And they get to sit down pretty quickly. So they do that. I've seen other ones where they say if you do every other row, somehow that spreads people out enough. I don't know. The best one happens to be if you can open 2 doors on the plane, the back door and the front door, and you let people go in both. Saves a lot of time, as it turns out. But you don't see that very often. You can get off a plane a lot that, but you don't get on a plane too many times with both doors. Anyway, priority. Okay, it's all about that. OK, so a priority queue stores elements according to their priority. I don't think that would be too surprising, right? And not in a particular order. Okay, this part is the important part. There does not need to be a particular order in a priority queue from the abstract data type or interface perspective. Who cares what the order is? And we'll see why in a minute. Okay, but this is fundamentally different than the other data structures we've talked about so far. In particular, the array, and in particular, the linked list. Because both of those have this idea of where in the list are you. Are you the first item? Are you the last item? Are you somewhere in the middle? For a dynamic array, for instance, you can pick out a position. You can say, I am at index whatever. Right? So that's different than this idea of saying, you've got a priority. You're somewhere in the list. When we need you, we'll find you by priority, and we'll return you. OK? There's no real notion of position. OK? All right. I'm seeing people furiously writing some of this down. You can write this down. It is also online. Don't forget. Yes, James.
I mean, couldn't you just do an array of structs that have a priority number?
Could you do an array of structs that have a priority number? You certainly could. In fact, we've kind of already seen that a little bit, right? I mean, our events for our calendars, they have a start time, which is what we're using to drag all the other data along, the description and all that, right? You could call the start time the priority in the sense that earlier start times need to come out first. Now, we've been ordering them, but it's really the same idea. Yeah. Any other questions on kind of the grand idea of these things? OK. All right. So when you're talking about priority queues, we have to get into this idea of a key. OK, anybody programmed in Python before? A couple people? Yeah, a couple people have. In Python, you'll get used to these all the time. Python loves this idea of dictionaries, which has a key value and some sort of element or value that's associated with that key. All a key is it is a way to, it is the part of the structure or whatever you're using to do the priority that is the priority, right? So the key, OK, is what you use to rank these objects to say which has the most priority, or the highest or lowest priority, right? Not limited to priority queues. In Python, they use them for dictionaries, even for things called maps in other languages, which is really the same thing. They use them for hash tables and all this stuff that we will talk about later. Okay, keys are not limited to just priority queues, but this is really the first time we've talked about them. Keys are not necessarily unique. 2 items can share the same key. Okay? As it turns out, not in some data structures, but in a priority queue, that's all right. What does it mean for 2 things to share a priority? Well, they have the same priority, and you don't get to determine which one you get if you ask for one of a certain priority. It just gives you one. Whichever one happens to give you, then it will give you. There's no other priority. If you wanted to have one before the other, what should you do? Give it a different priority. Yeah, OK, so you can't do that. Now, keys aren't necessarily unique, which means you can have different keys for the same thing. They also can change. So let's say we've got some program that's ranking restaurants somehow, right? Well, you can rank restaurants by a number of different ways. You can say, hey, let's look at the Yelp rating, right? Let's see how it does in Yelp. If it's got 4.5 stars, that's going to be the first one. Or you could say, you know what? I'm looking for a cheap meal, and I want cheap whatever food, right? and I don't care about the rankings, I just care about it being like food in my stomach for less money, then you could rank it by how much stuff costs, right? And Yelp has that too on there. It says how much things cost, and you can re-rank by that. Okay, but that means that the key can actually change. The type of key can actually change. You can't change a key once an element is inside the priority queue. The only way to do that is take it out, change its key, and put it back in. It's the only way you're allowed to do that. Okay? By the way, ratings are an interesting one. Ever go to Amazon.com and you'll look up a product, and it gives you the products kind of by rank generally. It tries to give you the ones that are highest ranks. And sometimes you'll notice, you'll be like, wow, this one got 4.5 out of 5 stars. And you'll look down at the reviews, and it'll be like 3 reviews, right? Like 2 people get a 5, 1 person got a 4, and and it's still got this great rating. But not many people have actually ranked them. That's because Amazon probably doesn't use the best ranking strategy or strategy to give you the results. What should they do instead? Use a compound of what? Yeah, they should probably say, hey, there's some threshold here of number of ratings before we'll say that this product's awesome. Like maybe it has to get 10 ratings before we'll say it's great, right? And so they should have some threshold. I wish they would implement that, because then it would, move out some of those things that get only a couple good ratings, and who knows what they really are. So there's lots of research into that too, by the way. Okay, so that's what keys are. Now we have to get into a little more detail about keys. Okay. Keys, as I said, can be more than one value. Well, the passenger one's a good example on a plane. If you're competing against or comparing against other passengers for a standby seat, they might check the fare paid, the check-in time, frequent flyer status, all that to determine what your priority is. Okay, it's not necessarily just one number. It can be many different numbers. Keys can be generated by the property of the object itself. Like let's say you're trying to rank the cost of books. Well, the cost of the book is what the key would be, right? If you happen to want to get a car that's not very heavy so that it gets better gas mileage or something, you could rank something by the weight of the car, right? And that's just saying, hey, some property of that object is what I'm going to use to do as the ranking, as the key. Or you can generate it from some other algorithm, like the priority for the gate agent who gives you a standby ticket. When you walk up and say, hey, is there any standby seats? The gate agent's like, hold on a sec, and starts typing your stuff in to find out all this stuff about you, so she can make this decision about whether or not you're, you should be 3rd in line or 10th in line or whatever, right? So you can generate them different ways. Right? How do we actually compare keys? Now this is digging a little bit more into the details. If you're comparing integers, you do not have to worry about this, because integer comparisons fit into this strategy I'm going to show you very nicely. But let's say you're comparing other things. You have to have a way to do the comparison, right? Whether it's rankings or 5-star rankings or some sort of cost or some amalgamation of the two. Once you come up with a priority, you have to be able to compare them in the following way. There's 3 priorities. It's kind of mathy. There is the reflexive property. The reflexive property says that if k is k is always less than or equal to k. That basically means k equals k, right? But in other words, if you're doing a ranking, if you're saying what happens when you compare k against k, you will always get that it is less than or equal to itself. It'll definitely be equal, but we're going to use the less than or equal to comparison model here. It's kind of like what we did with our is before or am I before function. Remember how we said if it's before, it shouldn't actually, it shouldn't go before. If it's the same time, it shouldn't go before, it should go after. It's kind of the same idea. We kind of flipped it in this one. But yeah.
So does it sort of leave room for other like qualifications to?
Well, all we're trying to do is get some things that are non-contradicting. So whenever you do 2 comparisons, everybody will agree that these things are true about them. Take 2 items, you say this one is less than or equal to this one. If they happen to be the same one, that is true. We will all agree that that's true if they're the same item. That's all we need to do. It does leave it open a little bit. But take a look at the other properties for a minute. There's an anti-symmetric property which says if k1 is less than or equal to k2, and k2 is also less than or equal to k1, well, that means they have to be equal. So far, so good? It's not rocket science, right? If that's true and that's true, then they have to be equal, because there's no other way to have them both be less than or equal, less than each other. And then finally, there's this property that says, and this is the one that you might have thought first if I said what kind of properties do you need. If k1 is less than or equal to k2 and k2 is less than or equal to k3, then k1 has to be less than or equal to k3. You can't somehow have this one less than this one but greater than this one. It's not going to work. Okay? It's just when you're comparing. Now, this is not a big deal when we talk about integers, which is what we're going to talk about most of the time. But you just have to be wary that this is an issue. When you're comparing floats, these things are tough to generate properly, right? Because it's not necessary. Because two numbers could be less than or equal to each other, but they're not actually equal to each other, or they should be equal to each other. It gets a little crazy when you deal with floats, which we've talked about before. Okay? Questions on this? All right. So our comparison rule here, what does it do? Well, it gives us a linear ordering relationship among a set of keys, meaning that you will be able to order keys from the minimum and on up. Basically, it means there is a minimum smallest key. That key could be shared among different elements, right? So you could have a lowest key, but it's shared among different elements. That's fine. But you will always have a lowest key. Okay? And that's nice because that's all we really care about in terms of getting some values out of this priority queue. Okay? All right. So what do we have in this case? Smallest number, smallest key. So what is this priority queue? Let's go into a little more details about the priority queue itself. Priority queue is what? It's a container of elements. Have we ever seen those before? We see them all the time in this class, right? Lists are dynamic arrays are containers of elements. Linked lists are considered containers of elements. Trees are considered containers of elements. This is another container of elements. Now, you can build a priority queue out of a linked list or out of a dynamic array. In fact, we'll do that a little later. So you'll see that. And it's just each element has a key that is provided when you insert it, and that key determines the priority. That's all there is to it. Okay, the key determines the priority in picking those elements. Okay. All right. There's always operations that go along with these data structures. We have three main operations here that we're going to care about. Operation number 1 on a priority queue P is insert item. Looks familiar. Remember, for things like stacks, we only had a few. We had push, pop, and top. Those are all the only three we had for a stack, which made it nice because we could do certain things they're easy to do with stacks, and you get very fast access time. Same thing here. We've got insert time. You give it a key, you give it an element, and it inserts that element with that key, that element with the key into the priority queue. Does it have to be in order? No, we don't care. We don't care in the sense of the data structure. We might care in the implementation. In fact, we'll certainly care in the implementation to some extent. But we might not order them. We don't need to order them. We've also got min element. That says, give me the element with the smallest key. If I'm ordering the elements, the smallest key in this case is going to be the highest priority. I guess we could have said the highest key is the highest priority, but now we're just saying if it's lowest key, the highest priority. Okay, it's like ordering people in a line, year 1, year 2, year 3, you're the highest priority. You can't get the max element. You can't get any other element. Not allowed. All you're allowed to get is the minimum one. The top priority one, that's the only one you're allowed to ask about, the only one you're allowed to see. Technically, you're not allowed to print the elements out in the order that they happen to be in. You're just not allowed to do that. Okay? The function I write later, you will be able to see it because I want you to be able to print it out if you need to. But in terms of being able, the data structure itself, you should not be able to print it out. And then remove min. This actually removes the smallest element. Min element tells you the smallest element. Remove element gives you the smallest element. Can you write a method that actually does both in one shot? Sure. You could. It would call min element and then remove min, and then you'd return the element. That's all it would do. Easy enough. And remember, more than one element can have the same key, and you don't get to decide which one you get. If it happens to have the same key, you get one. That's what happens. Okay? Delete is kind of the same one. Remove min, sometimes you can say, some implementations will remove just the first one, whatever it decides the first one is. Not the first one by when you entered it, whatever it decides first one is. Some implementations will delete all of them, for instance. Okay? And some implementations actually don't allow you to have multiple keys, but most do. Python doesn't in certain cases. Okay? This makes sense, the top three here? They're not the only operations, of course. We've also got other operations that we've had in lots of our data structures. These ones aren't as important, though, because we're not going to worry too much about them. The size, you just keep a number that says how many elements are in the priority queue. Is empty, that just tells you if it's empty. If there's no elements, you return true. If there's some elements, you return false. Min key, this is an interesting one. This one returns the smallest key to you, right? So you put a bunch of elements in there, and then you say, what's the minimum key in there? All right? Why might you care about the minimum key versus the minimum element? Any ideas? Vivek? Yeah, if you want to insert something that's higher priority, right? If you were a hospital and you started prioritizing people and then 10 people came in and you only had 10 priorities, and you said, well, I guess you're number one, and then some guy comes in and his neck is bleeding out an artery, right? You're not going to say, well, there's no more priorities, or I don't know what you're going to reprioritize, and you're going to say, this guy's now 0.5, right? Because he's in now, right? You can definitely do that. So you definitely have reasons where you might need the key. Did you guys watch the Olympics this last couple weeks? Some of the Olympics? I only watched a little bit. And I don't know if they still have, it still kind of works this way too much. But figure skating's always been this way, where you have the first couple figure skaters, right? They might skate almost perfect routines. Do they ever get the highest score possible? No. The first couple never get the highest score possible, right? Even if it's like, oh my gosh, I've never seen a better skater than that. If you're the first one, you're not getting the highest score. Why? Because somebody else might come along and have an even better run. And then if you gave them the highest score, well, how are you going to give the net? You can't say, well, you tied. You just can't do that, right? You have to say yours is actually better. So you need some room at the top. And so that's why you might want to say, hey, what is the minimum key so I know how to prioritize other things? Okay? That's, again, the only one you can do. Yes?
When you take something out of the priority queue, do you need to know its key?
No, you don't. Once you take it out, you don't need to know its key. If you want to know its key, you have to call min key, and then you call get min, or whatever it was. It was min element, right? You call both to do that. Yeah. Yes?
Is min key the minimum possible, or is it the minimum that's on the list?
It's the minimum on the list, not the minimum possible. Yeah. Yep. In some cases, you shouldn't have a minimum possible, although you really always will, but you shouldn't necessarily have a minimum possible, right? Or you have to reprioritize if you need to do another one that's higher and whatever. Yeah. OK. All right. So what this means, by the way, is the constant reference part. It says returns a constant reference. What that's saying is you can get the key, but you can't change it, right? You can't go and change that key until the only way to change a key for an element is to take it out of the priority queue and then insert it back in the priority queue with the new priority. You could come up with some other way to do it, but you'd have to reprioritize in your inner structure. You don't want to have to do that. We're trying to make this as simple as we can so that we can use it to very effectively. Okay? Questions on that? All right. So priority queues are therefore simpler than regular old sequences. You don't have to do insert before, insert at the end, insert at the beginning, right? You don't have to have special cases like that. All you're doing is inserting, right? And then you don't have a separate delete functions for saying delete at the end, delete at the beginning, all that stuff. No need, right? Don't need to worry about that. You may need to worry about, well, you don't need to worry about that in particular for the priority queue as a data type or abstract data type. Okay? Kind of cool, kind of nice. It's simple. Kind of like our stack and our queue are relatively simple. Okay? So here's an example. So let me go through this example. It's kind of quick. It's not too hard to understand. What I'm going to do is I'm going to put a bunch of operations into it. You're going to apply a bunch of operations on this priority queue, and you're going to see what it comes out as. Okay? All right. The first one, insert 5a. 5 is the key. A is the element. You don't get an output when you do an insert, and your priority queue ends up saying just 5a in it. Not bad. Okay. You do a couple more. You do a few more, actually. Insert 9, insert 3, insert 7, C, B, and D. Notice I don't care what order they're in this case. 5 goes in, then 9 is there, but then 3 goes in, so it's over there. It doesn't order it, certainly doesn't order it by the elements, and it doesn't order it by a priority. It doesn't have to be. For the data type, it does not have to be. 7, same thing with 7. OK, now I say min element. Well, it goes through here and it says, dun, 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 where's the min element? There it is, and do that. How long does it take to find the min element here? What is our asymptotic notation for that? It's linear, which means O what? Not O1, ON, because the only way you can do this, well, if we're doing this with a list anyway, the only way you can do this is you go, is that the minimum? No. Is that the minimum compared to that? No. Well, it is. Yeah, this one is so far. That one, nope. That one, yeah, now it's this one, that one. And you have to go all the way to the end. You can't beat it in this case. Now, if we order it some way, well, you could, but we'll get there. OK. Min key. Well, the min key is 3, because B happens to be, this is the min element, and its key is 3. Okay. All right. Then we go to remove min. 3, what was it? 3B was the minimum. It removed it. Did not give you any output. Gave you the new priority queue. Straightforward stuff. Size, easy enough, 3. Min element, same thing. 5. The min element is at this key, so it's A. Remove min. Now it's down to 9 and 7. Remove min. Now it's down to 9. Remove min. It's empty. What if we tried to remove min again? It depends how you define it, but generally it's an error, right? Yeah, in this case we say it's an error. Now your program, if you built this, your program could either say, hey, you've got an error, you can't do that, or it could return a value that says null or something, whatever you're trying to return, or it could actually have an assert and fail. You know, the person using this data structure should be the one who's checking for that is empty. So you need to call is empty on these things, so you should call is empty and it will return true. OK? All right. Any questions on what a priority queue looks like from a data type, abstract data type, data structure perspective? I don't think this is that bad. This one's not too tricky anyway. OK. Let's go ahead and implement one. OK. Let's implement a priority queue using an unordered list. Are we allowed to do that? Why not? Right? We have seen things like this a lot, right? Where you have a little struct and it's got a couple different things in it. Well, this just has the key and the element, and that's what we're going to use. We're going to call it a priority object, and that's what we're going to do. Okay? Let's see some of the other public functions. You've got, well, I'm going to do it with a dynamic array, so I've got a capacity. You've got the constructor. You've got the size is empty, insert time, min element, min key, remove min, and I stuck this one in there because if you want, you can see what it looks like. But you shouldn't get access to this if you were going to publish. You shouldn't give access to that if you're going to publish it, because they're not supposed to, the person using your class shouldn't know about that. Let's look at the private elements. Private elements, and this code is all of mine, by the way. It's kind of ugly right now because of some of the things I did so that later stuff will work, but it's there. In the private part of the definition of the class, we've got just the queue array. It's a dynamic array. We've always had those. We've had those a lot. We've got the size. We have the capacity. Shouldn't be too, or should be very familiar. I've also put the expand one in the private, and I've also put this one. This is an interesting one. Because I'm using a dynamic array, it's not a bad idea to, in the private section, be able to get the index of that element. Because you don't want to have to call min element and then, well, let's say you don't want to call min element and or have to rewrite the code for min element and the code for min key or whatever. You'll see why it's important in a minute. Okay. All right. So those are the functions. Let's implement some of the objects. Yes.
So what if you have two elements of the same min, which is just randomly choosing one of their indexes?
If you have two elements of the same min, you don't randomly choose them, but however they end up in your data structure and however you decide to pull them out, that's the one you get. Yep, that's the one you get. And you have to deal with that. If you need them to have priority over each other, give them a different priority, right? Okay. So that's what that looks like. Let's write some of these operations. Okay? For insert item, here's what it looks like. Insert item, okay? And it says it checks for capacity and expands if necessary. Okay. And then because we're not doing this ordered, well, we're using a dynamic array. Let's just stick the item at the end so we don't have to move anything. Right? I know you get sick of moving stuff right back and forth, and it takes time. Just stick it at the end. So all we do is we say P, we say the priority queue size, we put the element in the priority queue at that index. We put the key there, we put the element there, and we increment the size. What is the asymptotic, what's the word I'm looking for? What is the big O notation for this? What is it? O of 1. Yeah, let me write some of these things down, right? This one, if we are doing insert item, K and E, okay, for an unordered list, okay, it's going to be O of 1. What did I say about O of 1? Why is it O of 1? Do we need to know how many elements are in there? Nope, we just put it right at the end. Sure, you've got to do some checking. You might have to do this expand, which could take a little while. And yeah, that does copy things, right? But it only does it every so often, and it only does it kind of on a logarithmic kind of basis, right? So that's not too bad. In this case, so these little things only happen once, and so it's order 1. That is the holy grail of big O notation. We love that, right? Where is it? Yay, right? We like the fact that this is order 1. That's awesome. That means it's really fast to insert, which is great. Okay? All right, questions on insert item? No. Let's look at MinIndex. Okay. The MinIndex function does what? All right, it sets the minimum index to the first, and this is just the, well, before we look at, we're really looking at min element. Min element here is going to call, say, return the priority queue at the minimum index. Because the minimum index is what the index value that you're looking for of the minimum key, or the minimum element. But the MinIndex function does this. Sets it equals 0, goes from 1 to the size, and loops through. And every time it checks and says, is this the minimum? If it's not, if it's the minimum. If it's not, set that index to the minimum index. All it's doing. We actually wrote this function last week when we talked about doing the asymptotic analysis, right? Remember this one? It was, I think it was called min item or something like that, right? It's just saying that, and then it returns the index, and then this function returns this. What is the big O notation for this? What is it, Susie? It's big O of n. How do you know? And what's the for loop say? It goes through each one, right? It goes all the way from the first, well, from the 0th one here, and the loop itself goes all the way to the size. Can it skip any? Can it ever say, hey, I'm only part of the way through, I'm done? It cannot. There's no way to do that in this case. Now, a lot of times you skip this instruction, but as far as the big O notation goes, for min element, right, we have O n. And O n is not terrible, but it's not great, and it's not great enough to get a boo, right? We don't love the fact that this is order n. We have to go through every element to get to the minimum one. That's not the best data structure, like not the best way to do it, and we can hope. Okay? All right. Let's see, we also have to remove min. How do you do remove min? Well, you start at 0, or well, you check and see if it's 0, and then you give this error business, if it is, because you can't remove from an empty priority queue. Then you say, OK, our min index, same thing. We're going to use that min index to find the minimum index. Okay? And then we are going to go through the list, and we're going to go from that min index, right? And then we are going to count up and go all the way up to the size minus 1, and we're going to delete and move all those little elements, all those elements back over. Because when you remove something from a priority queue, okay, you need to remove it and fill in the blanks from a list anyway. What is the asymptotic notation for this one? What's that? Still order n. Now, you can argue that this is worse than order n because, well, this finding the min index business has to go through all of them, right? And you have to go through all of them. Then you have to go and find that one again and move it. And so, yeah?
Don't we almost have the minimum index in our private?
Why would we have the minimum index?
I thought we made a function to store it.
Ah, well, OK, so we didn't.
Okay.
We didn't store it. We found it. Like there's a function that's min-index that finds it, right? We could store it. Would that help us? If we stored it, then how long would it take to get that minimum index?
The first time?
The first time, yeah, the first one, and then we just have to change the queue. That wouldn't be so bad. What's the problem with that?
You have to change it every time.
Yeah, you'd have to change it, and you'd have to go and find the next one. So maybe you could get it instantly on your first shot, but then your second shot around, you wouldn't. That might not be a bad idea in some cases, right? Like let's say you've got, let's say you're doing something where you want to get the return value, but then while that somebody's looking at that value or whatever, you're doing some processing in the background. That's an easy way to get it, right, like that. Then in the background, do the processing. So that might not be a bad idea, right? This is not really the best way. In fact, you could argue this was O(n) squared in some cases too, because it's got to go through the whole list and then delete it, right? So it's not that great. But we'll call this order n because in the average case, in this, it's going to be order n. OK? So this is going to be remove min, right, is going to be order n. OK. Which again gets a boo, because it's not so great. All right. What's another way to do this? Priority queue. Keep it ordered, right? When we did the calendar thing, we kept it ordered, didn't we? Well, can we do the same thing with this one? I don't see why not. Let's build the same thing using an ordered list. Okay, we kept the list in order. In our calendars, we kind of kept the list in order by the key, which was the start time, right? We kind of did that. Okay. All right, well, if you want to keep it in an ordered list, you'd better do some work to keep it ordered when you insert it. Right? I have to bring the whole stupid projector screen down to show you all this, right? Remember how it was kind of tricky to do that? You guys had to write this, right? And you've done this before, and it was painful, right? The first time you did it. All right, so what do? You expand if you need to. You check the special case for the 0. If it's the 0th element, you insert there, right? Then you keep it ordered. How do you keep it ordered? You walk through the list, right? And then when you find the place where it goes, then you do another little loop here from that place to the end, and you move everybody over, and then you stick the element in there. This should not look unfamiliar at this point. But it's kind of a lot of work. I mean, you know, there's a lot of little stuff that goes on here. And you've also got that case at the end, and you've got to do some returns. By the way, I had a little bit of an epiphany today. We are writing too many for loops. This probably should be a while loop. We should probably get in the business of writing more while loops and less for loops. I might rewrite this to do that. Because for loops should only be when you know exactly how many elements you need to walk through, not when you have some in this case. So maybe we'll talk about that later. But anyway, point is, this is not the easiest thing, but this is going to save you, right? Because now that it's ordered, we're going to have lots of benefits from that. OK. Question, what's the asymptotic BigO notation? Oh, yeah, question, Sam?
I was going to ask if there was a trade-off between for loops and while loops.
Is there a trade-off between for loops and while loops? Not really. They're more or less the same thing. In fact, the compiler pretty much does the same thing. For loops are kind of an easier way to write while loops, and they're generally for when you know the number of elements. Yeah. No other real trade-off. OK, what's the BigO notation for this? N squared? Why would it be n squared? Are you thinking, hey, there's two for loops and they're nested, and so it's n squared? Yeah, that's not a bad thought, except keep in mind this part, and it goes to what I was just saying about while loops. This part goes through how many elements? I don't know, enough to get to the one where you need to insert it. And then this loop goes through the rest. So you see how it's not really nested so much? And it also, by the way, returns. So it's not nested so much. It's like breaking it into two parts. So not O(n) squared, but O what? O(n) again. OK. So I'll write that down here when the board comes up. And yes, it's BigO of n for insert. OK, BigO of n for insert for an ordered list. Ordered list. All right, so that's our first kind of trade-off, but it's going to get us something, we hope. Let's see what it gets us. Boo. There's a boo there. OK? All right, well, now our min element. So we have just ordered this, and what we're going to do in this case is the last element is going to be the highest priority. OK, and the highest priority is going to be the last element. Look at our min index. Remember before the min index was like that long and it had to loop through and it had to loop through all of them and whatever? Our min index now says return size -1 because that's the minimum one. We made it that way. We said the last one is the minimum one. Wow, that's great, right? That whole function now it's boom, just like that. And then this one still, I didn't even change this one. It's the same exact thing. It just returns the priority queue of the min index. What is the asymptotic notation, big O notation for this? What is it? Big O of 1. Right, we got our first benefit out of this. Right, so this one is big O of 1. Woohoo! It's great because we don't have to change anything. Or we can get rid of all this stuff. We don't have to change this part. We can get rid of a lot of stuff. Good to go. So we get a yay for that. OK? All right. So let's see. We've done insert. We've done min index. We've got to do remove min. Well, guess what? You still have the same thing here. In fact, I didn't change this at all. Does that mean it's still on? Min index, we get the index here. How many elements am I going to have to walk through to move if it's the last element? 0. This is irrelevant. In fact, I should just take it out. Right? It's going to always, the min index is always going to be this PQ size, the priority queue size -1. So this loop isn't ever going to run, and it's never going to need to move anything. That's awesome, right? We get this great benefit. What's the big O notation for this one? 1 again. All right. So now we've got big O of 1 for that. And now our ordered list seems to be doing all right. Not bad, not bad. Let's see. Let me show you what how this actually works. I coded this up this morning. And here is what it looks like. Let's see. Nope, not this one. Where was it? There we go. OK. So what I did was I had the computer take that word list that we got earlier from A-spell, and it takes the word list and it prioritizes all the words in it by their alphabetic notation. So all the A's are high priority and all the Z's are low priority, right? And it looks kind of like this. Let's see, less word priorities.txt. It looks like this, right? I randomized it too, right? So I said all those. So I said hearsay, right, is word 83,084, right? And there's 230-some thousand elements in here, right? If you look at something with a like Small's word, whatever that is, right? 183,000, because it's near the end of the dictionary, right? And let's see, D's are kind of near the front, so on and so forth. So it just does this, and it randomized it. And I just said they're all in random order, but now you've got a key and an element. OK? All right. Was there something funny in there? I didn't notice that one. All right. So anyway, so you've got that. And what we're going to do is I'm going to run the ordered list, or the unordered list program, and the ordered list program. And what it does is it reads in, both programs read in all those dictionary values, all 235,000 of them. And then it removes 1, then it removes 10, then it removes 100, then it removes 1,000, then it removes 10,000. Or maybe it does 1 and 100. It might skip 10. But anyway, then it removes 10 up to 10, then it removes 10,000 of them. And it times it, kind of like what we've seen before. And the first thing it's going to do is actually, when it's reading them in, as it's inserting them, it's going to put down, it's going to say a number when it gets to a multiple of, I believe it's a multiple of 1,000. OK, so it will go, you'll see 1,000, 2,000, 3,000, 4,000, 5,000, all the way up. OK? All right. This is going to run, the first one I'm going to run is the priority, let's see, priority queue unordered. Yeah, unordered on the word list. Now watch what happens. Okay. All right. Da-da-da-da-da-da. It goes through. Did you see how fast it put all those in there? Went flying through there, right? And then, so it took 1.3 seconds to insert those. And then the size is 235,000. To remove one took about 4,000ths of a second. To remove 100 took 2.28 seconds. To remove 1,000 took 2.8 or 2.9 seconds. How long is it going to take to remove 10,000? How much? How about 28? Yeah, around that maybe. 29, 30, depending on where they're located in the array, because there's a multiplication factor in there. And there we go, 33 seconds to remove that. Okay, so did we kind of see this? We saw inserting very fast. Finding or removing, kind of slow. Okay, all right. If we now run the other one, let's say I was to go ahead and run the same thing, the ordered list on the priorities. Watch what happens. Okay. All right, it's going down there, and it's going, and it's going. Can you notice anything about this? It's getting slower and slower. Look at this. It's like starting to crawl a little bit, right? Oh, what a pain. All right, when it gets to like, in this one, I did it on my computer at work, or at the office. When you get down to like 200,000, like, hurry up already, right? Because it's like click, click, right? Because it's got to go through, it's got an increasingly longer list that's increasingly harder to, or increasingly longer to look through to find where it needs to insert. And then it's got to move all those elements. So that's why it's slow, 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 right? You don't really want to wait for this. It took something like 3 minutes or 4 minutes on here to do it. Yes?
So even looking at the board to see how they will either unordered or ordered both ways have, you don't really gain. Is the zero end there, it's also zero end here, but they're not really equivalent because the insert before is taking way longer.
Yeah, they're not equivalent. Now, we generally try to not compare BigO notations to each other in the same, for the same BigO of n. We will in some cases. Like some algorithms have a slightly better, factor. Like this might have a factor of 5, and this might have a factor of 3, and that means it's going to be that much slower and that much faster, right? But anyway, so I'm not going to make you guys wait for this one. Although what I did was I cheated a little bit. I actually came up with another one that I ordered, right? Oops. Let's see. In order. Actually, let me do this first. Here's what I'll do. If I do the in order, if I look at word list, or hang on, yeah, word priorities in order, right? I did it backwards so that it only has to go to the front and then insert, or it inserts it all the way at the back, I guess. Or maybe I did it the other. Did I do it wrong? Wait a minute. It should insert. Yeah. It's OK. It does this one, then it does this one, which inserts. So it doesn't ever have to move anything. OK? Because all these words, I have no idea what half these words are. But, or for that matter, any of them. Well, anyway. How far down do you have to go before Chris understands a word? OK. So anyway, if you do this, now this one will also slow down, but it is noticeably faster, right? It's noticeably faster. It's not amazingly fast, but it's faster because I cheated a little bit. So this really goes back to your point, Margaret, that this big O of n is not equivalent to this big O of n in some sense. Although we didn't try to remove all of them, which might have taken a long, long, long time. We only removed 10,000 of them, and that took 28 seconds, right? So if we were trying to move all 235,000 of them, it will get faster as it goes along because there's fewer items in there to remove, but it is not great. So let's see. I've still got some time. I got to learn to tell jokes. Do this stuff, right? Someday I'll tell you my army jokes. So anyway, so it's going to get up to 235,000. Now, how fast should it do the deletes, the removes? 0.1 for removes. It should be done really fast, right? Let's see if that comes out that way. Okay. Where do we find the dictionary? Hang on. Let's have one sec. Look. To remove 1. It can't even tell how fast it was to remove 1. It was so fast. The timer I used, not fast enough. Right? To remove 100, it took 9 microseconds, I believe that is. 1, 2, 3, 4, no, not even. I think it was like 0.9 microseconds, right? To remove 1,000 took 6 microseconds. That is like no time, right? To remove 10,000 took, what is that, 60 microseconds? Yeah, that's like very little time. Why? Because it's just to pick the one off the end and be done, right? It only has to do that. It's so easy. Yeah, question?
Did you already show how you do the timing?
I haven't showed how to do the timing. It's in the code. You can see how to do the timing. What you do is you basically set up a little function that holds times, and then you call the time function, and then at the end of the function you call it again, and you subtract the two, and that gives you the amount of time.
So there's like a built-in time function?
There is, yeah. Yeah. See, you can see how to do it on there. It's slightly different on Linux versus the Mac, but it works.
Like it calls the system time.
Yeah, calls the system time. Yeah, and it's a pretty good timer. I mean, it tells microseconds, but it won't get nanoseconds or whatever, right? It's too fast. Yeah. To answer your question, /user usr/share/dict dict, and that should do it on there. Okay. All right. So you see how we got some trade-offs here, but is one better than the other? What does it depend on? It depends on the size. I don't know if that's the right answer. It depends on something. What does it depend on? Yeah. There you go. It depends on expected usage. Sorry, I cut you off? Yep. Yeah, so yeah, exactly. So if you're doing, it all depends on how you're going to use this. If you are going to use this priority queue in this form to do lots of inserting, but not so many lookups, make it an unordered list. It's very fast to do all the inserting. You're only going to have to look up some things. That's great. If you're going to use this for having a list that you need to do lots of lookups from, what's a good example of that? A dictionary, right? How many times does either Apple or the people who design Linux redo that word list? It's already sorted for you, right? I showed it to you. It's sorted. It looks, if you look at less/user/share/dict words, then it's already sorted for you once. Nobody has to resort that. They leave it sorted, and then it makes it nice. So you can use a regular old, you know where the minimum is in this one. Now, this isn't necessarily the best example for the minimum with this one, but you see that? Okay. All right. By the way, did you know that? Well, you can also do this. You can find words in this. Grep ard. What am I looking for? Ardwolf in /user/share/dict words. There it is. So, did you guys know there's an aardwolf? Yeah, look it up. I looked it up on Wikipedia. It's pretty cool. It's like an aardvark, except it's a wolf. Yeah. I don't know. Yeah, look it up. It exists. It's really an animal. So anyway, so usage is a big part of this. Okay, it's how you use it and what you might choose for this. Now, after spring break, because next week we have a review session and then the midterm on Wednesday, and then spring break happens, and you guys are all probably going someplace warm, which is nice. I'm not. After that, we will come back to priority queues and see if this is really the best way to do them in general. Okay? Any questions on that? Yeah, Dylan. No? Questions on that? Anything? Yeah, Susie.
I guess I don't know much about how you're going to use priority queue actually yet, but wouldn't you have to be kind of careful about what numbers you'll be assigning? Because if you assign something one, like you said, and then you need a higher priority, wouldn't you have to literally take every single one out?
Yeah, that's a good point. Yeah, so in a priority queue, you need to be careful about how you're actually doing those priorities. Yeah, you need to leave it open so that you don't have two priorities next to each other that can't be split somehow. That's probably a good point. Yeah, depending on the usage again. I mean, now with dictionaries, it's not that often you add words to a dictionary, so recomputing some of that stuff would not be that bad. But yeah, it's definitely, there are some uses which that model doesn't work so well for if you have too many numbers scrunched in together, too many different comparisons. Yeah, good question. Good question. Yeah, James?
Could you make the highest priority key the highest number? That way you have kind of infinite number.
Could you have the highest, you could make the highest number key the highest number available to you, you mean? Sure. The problem is, once you set a value to that, if anything else ever comes along that you think is a higher priority, right? You've got one guy whose neck is bleeding. You've got another guy who's like carrying his head in his arms, right? I mean, you know, whatever, right? You get like maybe you'll get a higher priority. So yeah, but you do have to be careful. I mean, you do have to be careful about that. But yeah, priority queues are used for a lot of different things like scheduling all the little processes that run in your computer. Some of them have higher priority than the other. When you move your mouse around, right? You want the mouse to move no matter what else is getting computed. So the mouse movement has a very high priority on your in your system, right? In terms of what, like when you move that mouse, all things stop so that pointer can go from point A to point B so that you can get feedback on that, right? That's just kind of the way it goes, right? So the timer on your computer, the timer needs to happen every nanosecond or whatever it is, right? It has to happen. If it doesn't happen, timing will be wrong. So you want that to absolutely have the highest priority, you know, whatever. So yeah, very, very good. Other questions? All right, I'll see you guys later. Hope you finish up the assignment quickly enough, and we'll see you later.